to the b. So our denominator would go here, and our numerator would go there. And this is for c not equal to 0. Next, we have that if we have that a to the x is equal to a to the y, where a is not equal to 1, so this is just not equal to 1. Then we have that x is equal to y. So using those properties, you guys can try this checkpoint. Okay, so let's start going over the solution now. So for this first one, we have 4 to the 5 times 8 cubed is equal to 2 to the x. So we know that 4 and 8 are both powers of 2, so we can write this as 2 squared to the 5 times 2 cubed. 3 is equal to 2 to the 9. So if you remember on the previous slide, we went over the fact that a to the b, the whole thing to the c, just a to the b times c. Therefore, this term is just 2 to the 2 times 5, and 2 times 5 is 10. And then 2 to the 3 times 3, and that's 9. So you have 2 to the 10 times 2 to the 9 is equal to 2 to the x. And if you remember, we have that a to the b times a to the c is simply a to the b plus c. So this here is just 2 to the 10 plus 9, which is 2 to the 19. Hence we have that x is equal to 19. So that's our answer to the first part of this checkpoint. For the next one, we want to evaluate 243 to the 3/5. So if you remember, we had that a to the b over c is equal to the cth root of a to the b. Hence, this is equal to the 5th root of 243 to the 3. And 243 is just 3 to the 5. So we want to find the 5th root of 3 to the 15, because 5 times 3 is 15. And this is just 3 to the 3, the whole thing to the 5. Hence the 5th root of that is just 3 to the 3, which is 27. So for the next part of the checkpoint, we want to find x and y if 12 to the 5 times 8 cubed is equal to 2 to the x times 3 to the y. So we can write 12 as 3 times 2 squared and 8 as 2 cubed. So this is equal to, we can split this up as a times b to the c is equal to a to the c times b to the c. So this is equal to 3 to the 5 times 2 squared to the 5. And this is 2 to the 9 because 3 times 3 is 9. So you have this is equal to 3 to the 5. And this is a 2 to the 10 because 2 times 5 is 10. And multiplying that by 2 to the 9, we get this is equal to 2 to the 10 plus 9. So this is equal to 3 to the 5 times 2 to the 19. Hence, we have x is equal to 19 and y is equal to 5. Finally, we want to evaluate 0.5 to the negative 6 plus 10 to the negative 3. So if you remember, when we have negative exponents, that's simply 1 over a to the b. So 0.5 to the negative 6 would be 1 over 0.5, which is 1/2, to the 6. And this is 1 over 64, because 2 to the 6 is 64. And this is 64. And then we need to add 10 to the negative 3. So 10 to the negative 3 would be 1 over 10 to the 3, which is 1 over 1,000. So our sum would be 64.001 because 1 over 1,000 is simply 0.001. Now you guys can try the second half of this checkpoint. Okay, so I'll start going over the solution to number 5 now. So basically we want to solve for x given this equation. So we can notice that 128 is 2 to the 7. So if this is equal to 2 to the 7, then this part inside the square root has to be 2 to the 7 times 2, which is 2 to the 14. Now, since this inner part is equal to 2 to the 14, we have that this part should be equal to 2 to the 14 divided by 4. And we know that 4 is equal to 2 squared. Hence, this part should just be equal to 2 to the 12. So we're left with this. Now, this part inside the square root should be 2 to the 24 because 12 times 2 is 24. So we have 8 times square root of 2 to the x is equal to 2 to the 24. So we can divide both sides by 8. And this is equal to, this is 2 cubed. So we have that the square root of 2 to the x is equal to 2 to the 21. And we can square both sides to get 2 to the x is equal to 2 to the 42, because 21 times 2 is 42. Hence, we have that x is equal to 42. Now for number 6. So we're given an equation in x, and we want to find the sum of the solutions. So we have 5 to the x squared is equal to, and we can write 25 as 5 squared. And using the fact that a to the b, the whole thing to the c, is equal to a to the b times c, this is equal to 5 to the 2 times 4x plus 3, which is equal to 5 to the 8x plus 6. Hence, we must have that x squared is equal to 8x plus 6. So, want to find the sum of the solutions to this equation and bring everything to one side. We get x squared minus 8x minus 6 is equal to 0. So to find the sum of the solutions to this quadratic, we can use Vieta's formula. So in general, the sum of the solution for this quadratic is negative b over a from Vieta's. Hence, for this quadratic, the sum of our solutions is negative of negative 8 over 1, because we have a is equal to 1 and b is equal to negative 8. So this is just 8. So that would be your answer for number 6. Now for the last one, again we're given an equation in x, and we want to find the solutions to this equation. So we have, remember that when we multiply a to the b times a to the c, we just have a to the b plus c. So this left-hand side would just be a to the x plus 2x plus 3x. Where a is 2. And then on the right-hand side, we have 2 to the x times 2x times 3x. Because remember, we have this. When we take a to the b, the whole thing to the c, we have a to the b times c. Hence, this is equivalent to solving x plus 2x plus 3x, which is just 6x, equal to x times 2x times 3x, which is equal to 6 times x cubed. So we can cancel the 6 on both sides, get x is equal to x cubed. So you can easily see that the solutions to this equation are 1, 0, and negative 1. To formally see this, we can write this as the polynomial x cubed minus x and find the roots of this by factoring. And so we have x cubed minus x is equal to x times x minus 1 times. So the roots are just 0, 1, and negative 1. So now we'll move on to logarithms. So the definition of the logarithm is that if we have a, b, and c satisfying a to the c is equal to b, where we have a and b are greater than 0 and a is not equal to 1, then we have the log of b with base a is equal to c. So let's look at an example. So we have 5 squared is equal to 25. So our a is 5, our c is 2, and our b is 25. Then we have log of 25 with base 5 is equal to 2. So basically, this number raised to this number should give us this number. So now we'll go over some properties. Our first property is that when we take a to the power log b base a, we should get b. So if you look at our example from the previous slide, we have 5 to the log 25 base 5 should be equal to 25. Basically, you can just think of these two a's canceling, so you just get a b. Our second property is that if we take the log of b with respect to a and add that to the log of c with respect to a, we should just get the log of bc with respect to a. So to see this, we start with this equation. So this is equal to, and we see this by using this first property, because this just b, this is c, this is bc, and we know that b times c is equal to bc. And we also know that in general, a to the x times a to the y is simply a to the x plus y. Hence, we have that log a, so we take the sum of the exponents. This is equal to this. So that's how we get the second property. Now for the third property, we have the subtraction of logs. So we can start, so we have a to the log over a to the log. So we have this because, again, we use this first property. This is b and this is c, and this is b over c. And you know that a to the x over a to the y is equal to a to the x minus y. So we get this property because we have log b base a minus log c base a is equal to this exponent. Next, we have that if we have the log of a power, we can pull out that exponent to get this. So you can basically just pull this out in front and multiply by it. So that's our fourth property. Similarly, we have our fifth property as if we take the log of a root of a number, so the bth root of a, as this is equal to the log of a base c. So this is follows from number 4, because if we were to substitute 1 over b here, we would get a 1 over b. And a to the 1 over b is just the bth root of a. Next, we have that the log of b over a is equal to 1 over the log of a over b. So basically, if we were to switch the places of a and b, we would get 1 over that. Next, we have that if we have log c base b times log b base a, this is equal to log c base a. So you can just think of this as canceling these two to get log a base c. Next, we have the change of base property, which is pretty important. So if we wanted to write log b base a, or log a base b, in terms of logs of base c, first we take the log base c of a, and we divide that by the log of b base c. So basically we just take this, so that's the change of base property. So if we were to take, we'll move on to the next property. Actually, that's just the same as number 7, I think, so we'll skip that one. Okay, so be careful to note that these are not true. We simply have that log a of b times c is equal to log b base a plus log b base a. And we don't have any of these. Although they look similar, we only have this. So in general, if you see a log without a base, that just means the base is 10. You might also see this ln of x, which is ln of x. That just means that the base is e. So now you guys can try to checkpoint using the properties we just discussed.
Just a thing, there is an issue of
You can ignore number 3.
because, yeah, there's actually no real answer.
Let us know if you need more time. Also, let us know if you need a hint or anything for any of the problems. Okay, do you guys want to go over the answers, or do you want to work on them for some more time?
Okay, I'll start going over the solutions now. So, to find this expression, first we can evaluate log 8 base form. So basically, we have that we want to solve that 4 to the x is equal to 8. And our x would just be this. But to solve this, we can write this in terms of powers of 2. So 4 is 2 squared, so 4 to the x would be 2 to the 2x. And we have 8 is 2 cubed. We have 2x is equal to 3. So x is equal to 3 halves. The reason I solved this equation is that we just get this from the definition of the logarithm. So we have this part is 3/2. Now we can use the property that the log of b base a is equal to 1 over log of. So we're just switching the base and the. So we have log 4 base a would be equal to 1 over the log of 8 base 4. And we already computed this to be 3/2. Hence, we have this is just 2/3 because 1 over 3/2 is 2/3. Hence, our sum is 3/2 plus 2/3, which is 9 plus 4 over 6. That's 13/6. So that's the answer to our first part of this checkpoint. Now, we want to estimate the value of the log of 96 base 1.1 given these two values. So first, we can factor 96 into 2's and 3's. So we have 96 is equal to 32 times 3, which is equal to 2 to the 5 times 3. Remember that the log of 8 times b is the sum of the log of a. Hence, for the log of 96, we have this is equal to log of 2 to the 5 plus the log of 3. And remember that the log of a to the b, we can pull this exponent out to give us the log of a. Hence, we have this is 5 times the log of 2 plus the log of 3. And we have 1.1 in the base everywhere. And we are given these values in the problem. And our desired value is 5 times 7.273 plus 11.527, as we have these values from the problem. And I guess for this part, we can use a calculator, but yeah, I'm not going to do the arithmetic right now.
Or you can also estimate it to be 5 times 7.2 is about 36, and then plus 11.5 is close to 48.
Yep, that also works. So now for part 3, we want to find how many real numbers satisfy x is equal to the log of a base 2. So there are actually no solutions to this equation, and you'll see why in the next section. So we'll come back to this soon. So now we'll move on to exponential and logarithmic functions. So the exponential function is f of x equal to a to the x. So we have x in the exponent, and a can be any real number. And then our log function is f of x is equal to log of x base a. So our x is in the top, and a is any base greater than 1. So we look at the graphs of these functions. So we take cases. If for the exponential function, if a is greater than 1, if a is equal to 1, and if a is between 0 and 1. So if a is greater than 1, we have that f of x is equal to a to the x is a strictly increasing function. So basically, as x grows arbitrarily large, this function also grows very large as x is in the exponent. Next, if we have that x as x goes to negative infinity, so x goes really small, then this function goes to 0. We can see this by using the fact that a to the negative x is 1 over a to the x. So if you look at the graph of a to the x, where a is greater than 1, so that would be this solid right graph. So in this case, we have y is 2 to the x. So we see that as x goes in the negative infinity direction, it goes very close to 0, but does not quite reach 0. So there's an asymptote as y is equal to 0. And then as x grows very large, we have that this function grows and goes off to infinity. So this function right here. Now, if a is equal to 1, just have f of x is equal to 1 to the x. And we know that 1 to the anything is simply 1. So our graph would just look like a straight horizontal line. Finally, if you have that a is strictly between 0 and 1, our function is strictly decreasing. So we would have this dashed red graph. So in this example, we took a is equal to 1/2. So this is our graph. So as x goes to positive infinity, our graph goes to 0. And as x goes to negative infinity, our graph goes to positive infinity. So again, we have an asymptote at y is equal to 0. So those are what our graphs look like for the exponential function. And this is of the graph y is equal to 3 to the x. This is 1/3 to the x. So as a increases, our graph or our function grows at a higher rate. So you can see the difference between y is equal to 3 to the x and y is equal to 2 to the x. So now let's look at the logarithmic function. So again, we'll take this cases where a is greater than 1, a is equal to 1, and a is less than 1. So when a is greater than 1, the function y is equal to the log of x base a is an increasing function. So again, we have an asymptote, but this time it's at x is equal to 0. So let's look at the graph of this function. So if we have a is greater than 1, so we took a is equal to 2, we have this graph. So you can see there's an asymptote at x is equal to 0. And then as x grows arbitrarily large, this function also goes off to infinity. Now when a is equal to 1, we have that this is undefined because our base must always be greater than 1. Finally, when we have a is less than 1, the function is in fact strictly decreasing and also has an intercept at 1, 0. So we have that y in this case, or we can look at the dash red function. We have this. So at x is equal to 0, it starts off at infinity, but the value is undefined at x is equal to 0, which is why we have an asymptote. And as x goes to positive infinity, this function grows very low and goes to negative infinity. So this blue graph is for base 3, and this dashed blue graph is for base 1/3. So finally, we'll go over some problem-solving strategies. So we have this example. We have these two equations in x and y, and you want to find the log of xy base 10. So we can split this first equation. So we can split this up as x times y cubed. So we have, this is log of x plus log of y cubed. We can pull this 3 in front, get the log of 10, or log x base 10 plus 3 times the log of y base 10. So this is equal to 1. Similarly, from the second equation, we have 2 times the log of x base 10 plus the log of y base 10 is equal to 1. We split this into x squared times 1. So now let's call this a. So we have a is equal to the log of x base 10, and b is equal to log of y. This step isn't necessary, but it just makes the equations nicer because we have a plus 3b is equal to 1 and 2a plus b is equal to 1. So now we can solve this system of linear equations. So we can multiply this top equation by 2 to get 2a plus 6b is equal to 2. Then we can subtract these to get 5b, because 6b minus b is 5b, to 1. So we get b is equal to 1/5. And plugging this back into the first equation, we have a plus 3b, which is 3/5, is equal to 1. So a is equal to 2/5. And we want to find log of x times y base 10. We can split this up as log of x base 10 plus log of y base 10. And this is just our a plus b by our definition. So this is equal to, we already solved for a and b. This is equal to 2/5 plus 1. Hence, our answer to this problem is 2/5. So now let's go over another example. So we have that log. So again, we're gonna call this a, this b. So we have a plus b is equal to 10, and a times b is equal to 16. So we can rearrange this to get a is equal to 10 minus b. And we want 10, so plugging this into the second equation, we have 10 times b is equal to 16. We could solve for b and then solve for a, but instead, we're gonna look at, so this expression is just the log of x base 10 minus the log of y base 10. So this is equal to a minus b. So given a plus b and a times b, we want to find a minus b. So we can do this by first finding a plus b squared, which is equal to a squared plus 2ab plus b squared. So this is equal to 10 squared, which is 100. Now we can minus 4ab from both sides to get a squared minus 2ab plus b squared. And we have the value of ab to be 16. So this is equal to 100 minus 64, which is 36. And this is a minus b the whole squared. So in general, given the value of a plus b and a times b, that's how we find the value of a minus b, by subtracting 4ab from a plus b the whole squared. So we have this is equal to 36. Hence, a minus b is equal to plus or minus 6. And we can throw out the negative solution. Get a minus b is equal to 6. Because since x is greater than y, we can throw out the negative solution. So next, we have this example. We have this equation in x, and we want to find the number of solutions. So we have a to the b is equal to 1, where a is this, and b is this quadratic. So when we have a to the b is equal to 1, we can either have b is equal to 0, because anything to the 0 is 1, except when a is equal to 0. Or we can have a is equal to 1, because anything to the 1 is also 1. Or we can have a is equal to -1, but then we must have b is even, because -1 to any even number is 1, but -1 to any odd number is -1. We have these three cases. So first, when we have b is equal to 0, we have 2x squared minus 9x minus 18 is equal to 0. Then for a is equal to 1, we have x squared minus 11x plus 29 equal to 1. Finally, we have x squared minus 11x plus 29 equals a negative 1. But then we must check that our solutions for x give us an even b. So this expression has to be even. So we can solve each of these equations. So using the quadratic formula, x is equal to 9 plus or minus 81 plus 4 times 2 times 18, because we have this negative sign here, and then divide that by 4. This would be 18 times 8. This would be 80 plus 64, which is 144. And 81 plus that is 225. And the square root of 225 is 15. So we have 9 plus or minus 15 over 4. So we have 9 minus 15 would be negative 6 over 4. And then 9 plus 15 would be 24 over 4. So the two solutions from this case would be x is equal to negative 3 halves, and then 24 over 4 is 6. Now moving on to our second case, we have another quadratic. We have x squared minus 11x plus 29 is equal to 1. And we can rewrite that as x squared minus 11x plus 28 is equal to 0. You can solve this using the quadratic formula or just factoring this as x minus 4 times x minus 7 is equal to 0, because negative 4 times negative 7 is 28 and 4 plus 7 is equal to 11. So you can just do this by writing out the factors of 28. So for this case, we have x is equal to 4 and x is equal to 7. Finally, we have this quadratic. We have x squared minus 11x, and pulling the negative 1 to this side, we have plus 30 is equal to 0. Again, you can write out the factors of 30 to see that is it just x minus 5. So you have x is equal to 5 and x is equal to 6. But now we must check that our values of x give us an even b. So when we put in x is equal to 5, we have that 2 times 5 squared minus 9 times 18. So this is our exponent. So this term here is even because we have it 2 times. This is odd because we're multiplying two odd numbers, and 18 is even. So you have an even minus an odd minus an even would be odd. So x is equal to 5 does not work. And then for x is equal to 6, we already have that as a solution, so we don't consider it. We have a total of 4 solutions. Okay. So we have this last example, but since we're running a little short on time, we'll take our 5-minute break now and then start the
Okay, we'll start the Kahoot at 3 o'clock. You guys can join the Kahoot now.
I don't know.
We're still waiting for 2 more people. We'll give them 15 more seconds to join. Okay, we're gonna start. You can still join in later on in the game. It is below. Okay, so this one you can add these two together, and that gives you log. Sorry, I don't have my tablet today. But the common denominator will be this. And then on the top, you have log base 6 xy, and if it's 216, then it's 3. So then you can solve for log 6x times log 6y. And Kevin also has a solution in the chat. Okay. Maybe winner is winning. Good job. Right, you should use the change of base formula. So whenever you have two logarithms in a fraction and they have the same base, you can use the change of base formula. Yeah, that one gives log base 8 of 128, which is 7/3. Okay, now Ren Kane View is winning. Right, so if you have a sum of logarithms, you can multiply the things inside together. So it's log 2 ABC. And then using Vietas, we can find out ABC by just doing negative 54/2, which is 27. So the answer is log base 2 of 27. Maybe winner takes the lead again. Okay, well, you just work from outside in. So log 3 of whatever's inside equals 2. That means whatever's inside equals 3 to the 2. So that's 9. And then that means x is 3 to the 9. You could also take a look at the answer choices and guess and check until you find one that works. Okay, 64 is 8 squared, so that means it's root 8 to the 4th power, and then times root 8. So that means root 8 to the 5th power gives 64 root 8, and the answer is 5. Okay. Maybe winner has a streak. Okay, just curious, what numbers did you guys get? So the numbers that should work are 1, 3, no, not 1, sorry. 3, 9, 27, and 729. Okay, so let's first find what 2x minus 7 is. So that would be 9 to the 3 halves. 9 to the half power is 3. 3 to the third is 27. And then that means we get 2x minus 7 equals 27. And if we solve that, that gives us 17. Okay, well, 49 is close. But remember when you square it, when you multiply two binomials, you also have the 2 times log yx plus 2 times log yx times log xy. Right, yeah, and you need to subtract that, which equals 2, and you end up with 47. Hey, good job. Right, you turn the -3 into a log, and then you just solve the equation after that. Right, so everything cancels if you put them all in the same log, and you're left with log base 2 of 2010. So 2 to the 11th power is 2048. So the largest integer less than that would have to be 10. Right, you have to be careful not to, whether you're rounding up or rounding down. All right, nice job. Right, you square both sides of the equation first. That makes the exponent 6x minus 6. That means if you multiply by the fourth root of 11 to the 8th power, you can add 8 to the exponent, and then that gives you 6x plus 2. And if you do that, it's 121 over 25. Maybe winner is winning. 4 more questions left. Nice job. Right, you can write it as an exponent, then undo the -3/2 to get to the right answer. Okay, so x plus 4 is equal to 5 to the third power, or 125. So x is 121. And then 121 is 11 squared. So the answer is 2. Okay, well, you rewrite it as exponents. Yeah, thank you, Richard. That was really helpful. Yeah, you can rewrite it as exponents. So that's 4 to the x equals 3. And then that means 2 to the 2x equals 3. Okay, and then to get to 27, you cube both sides. That means you have 2 to the 6x. Okay, so k is 6. Okay, last question. Maybe winner is still winning. Okay. This is similar to one of the past problems. First, you find what x minus 2 is. 9 to the 1/2 is 3. That means x is 5. 5 to the 4th is 625. So that means 625 to the 1/4 equals 5. So x is 1/4. Okay. Right. Congratulations. Good job to everyone. 27% correct. All right.